Okay, good afternoon and welcome, and thanks for being here. The idea is to share a little bit about green ammonia, green hydrogen, or green ammonia. And I wanted to start with a phrase from the book that we were mentioning from Jules Verne. If you read the book, you remember this was a conversation between the castaways in their, how was the name of, in their palace? And they were talking with the engineering guy, and they say, hey, it was the middle of the industrial era. They were burning a lot of coal to do all the machines work and all that. And they say, what are we going to do when we have no coal left? So once we have burned all the coal in the world, how are we going to get energy? And then he said, well, we will burn water. How water? Well, water, but using electricity, we will split it into its elements, and then we will have an energy source much more powerful than coal. This was 1875. And now, how many years later? 200, no, 150 years some. We're about to live that. So now let's start with hydrogen. Do you remember? It will look like a little bit of a chemistry class, but if you remember hydrogen, hydrogen is the most abundant element in the world. They say that about 3/4 of the sun are made of hydrogen. It's a odorless, colorless molecule, but with a lot of energy. So you have a lot of energy in a very small molecule. The thing is that it has a very low weight, so you need to compress it and have it liquid to have a lot of energy. But in terms of weight, it has a lot of energy. Typical way to produce hydrogen is through a process called steam methane reform. So you take natural gas and you use this process to produce hydrogen. Now, the only thing is that that process, coming from natural gas, as we spoke, produces a lot of CO2. Actually, today we produce about 60 million tons per year of hydrogen in the world, and that hydrogen generates the exact, well, relatively same carbon footprint than the whole United Kingdom and France together every year. But there's another way to produce hydrogen, which is electrolysis. You remember, it's getting water, as Jules Verne said, and splitting water into hydrogen and oxygen using electricity. Now, if you use green power or green electricity to do that process, then the hydrogen you're getting there, it's called green hydrogen because it has no carbon footprint. And the thing is that this green hydrogen revolution, it's enabling a whole new world in terms of energy that can be used for mobility, for heating, for fertilizers, for fuels, for chemicals, and so on, based on this new green hydrogen. The only problem of this green hydrogen is that it needs a lot of energy, a very big amount of energy, incredible amounts of energy. Actually, the process is not new, but it uses a lot of energy. That's why it's not very widely used. But on the other hand, we have seen that the power, that the electricity, driven by the renewable energies, has gone down dramatically during the last decades. So the cost of energy is going down and down and down, driven by the renewable power. And if you see the cost of some equipments like the PV modules, the turbines for wind, or the batteries, so the energy accumulation process, they all also are dropping their costs. So slowly, we are getting to the point that we will be able to use that energy at a very low cost and have a green hydrogen as competitive as the gray hydrogen. And many people say, this is a study from McKinsey, many people say that by 2050, we will have a whole new use of different uses for this hydrogen that will generate a new industry. Actually, for us, Chile as a country, it's supposed to be as large as the mining industry. So it's a very large industry, and also all these new uses will be driven by the green economy. So all those places where you have abundant and cost-effective renewable energy, you will be able to dream about having green hydrogen and green ammonia at a cost-effective price. So some of those places are, of course, one of those places is the desert in Chile. Yes, absolutely. And so that's why we came to this opportunity that we call green ammonia. And we were talking about green hydrogen, but now we're talking about ammonia. So what's the relationship? The thing is that ammonia it's one of the most important derivatives from hydrogen. But it is much easier to handle, to transport, and to store ammonia than hydrogen. Because in order to handle hydrogen, you need to compress it and liquefy it, and that's very, very costly and complicated. On the other hand, ammonia, it's a widely used chemical. It has an established network of logistic, of ports, of vessels, and so on. So it's widely used. And also, if you have ammonia, you can crack it back down to hydrogen, or you can combust directly ammonia in some new engines that are being developed, or some called ammonia energy fuel cells. Actually, if you see the trend of the developments or the uses that will be there for hydrogen, ammonia is among the first ones, because if you want to start giving volume to the new green hydrogen, one of the fastest way to do it is replacing the current uses of hydrogen. And actually, ammonia stands for 42, 43% of the current use of total hydrogen in the world. So if we are able to replace the ammonia with this green ammonia, we will already be replacing about half of the hydrogen consumption for green hydrogen. So it's one of the best places to start. And why? And what's the relationship with us at Enaex? What do we have to do with ammonia? It's our main raw material. And normally ammonia is imported from countries that have gas. So we import it from different countries that have gas and transform it. We store it, we unload it at our own terminal, ammonia terminal. We store it in our tanks, and then we transform it into ammonium nitrate. And then we use that ammonium nitrate, as you all know, to do the blasting services at the mining industry. The thing is that together with that ammonia, we are importing about 750,000 equivalent tons of CO2 per year. And that represents today about 90% of our total carbon footprint in the production. So for us, it's very important to try to attack that footprint. So these are some graphs or information about the expected cost for hydrogen in the future years in Chile. So if you see in the center, in the north, and in the south, and if that's true, we should be able to produce green ammonia as well as green hydrogen at a very competitive rate. So that's exactly our project. Our project is to stop importing gray ammonia into the country and produce our own ammonia out from renewable energies in the country, a local green ammonia. And that project, when we are able to do it in the final phase, we will reduce about 1 million tons per year of equivalent CO2. That's about the same carbon footprint of 360 of the large haul trucks in mining, or the equivalent to 300,000 passenger cars, just to have an idea. So it's a large carbon footprint. And that ammonia will be used by our plant, but also it can be used in mobility, in vessels, in trucks, in train, or for fertilizers, or as an energy vector for hydrogen. Let's see some numbers about the project. So the final project, or what we call phase 2, it's going to be a 700,000 metric tons ammonia plant powered by 2 gigawatts of electrolyzers, which is a big amount of electrolyzers. And you will need for that about 3 gigawatts of renewable energy to make those electrolyzers work. That's a lot. But we're convinced that by the end of the decade, we will be able to produce green ammonia and give our customers green explosives and a green blasting solution. But now, this is going to be by 2030, not today, because today we don't have the electricity cost nor the technology in the electrolyzers or the efficiency to be competitive. But we're confident that we'll be there by 2030, according to all the studies from McKinsey and the other consultants. But we don't want to wait until 2030 to do something. We would like to do a first step. And also we're convinced that the cost will drive down not because of years passing by at the calendar, but by real megawatts being used and tons being produced. So we want to do a first phase that we call phase one, of course, which is a much smaller project producing 18,000 metric tons of ammonia, fueled by 3,200 tons of hydrogen, and that's going to be about 25 or 26 megawatts of electrolyzers. The only problem, of course, is that if the large scale is not economically feasible today, the small scale is even worse. So we're doing every single effort possible to try to get support or grants or efficiencies to make this happen and not having to wait until 2030. One important point to make is that we already are operating an electrolyzer plant in Peru. Do you know Machu Picchu? Have you heard about Machu Picchu? Cusco is the city where Machu Picchu is located. There's a small town called Cachimayo, located near Cusco, and there is a very old plant. It's almost 60 years old that we bought 3 years ago, and it was originally intended to produce ammonium nitrate for fertilizers, and it then was used to produce technical ammonium nitrate for the mining industry. But that plant already does the same process. They use water, electrolysis, they split the water into hydrogen and oxygen, then we produce ammonia and ammonium nitrate. The only difference is that that plant is connected to the grid and not directly to a renewable resource, so they don't have to deal with the intermittence or the variabilities. But it's the same process, and we have been able to gain a very good experience running that plant. So, why do we think that this can be a very good opportunity? First, there's a very important point, is that the demand is already there. One of the biggest problems for green hydrogen and ammonia projects today is that once you have the green hydrogen, you need to use it in something, in a car, in a truck, in a vessel or something, and that's still being developed. On the other hand, if you build a truck, where do you get the green hydrogen? In this case, we're already consuming green hydrogen in the form of ammonia. So the demand, the offtake is already there. Also, we are placed in one of the best places in the world to produce renewable energy, and therefore to have one of the best possible costs for that green hydrogen or green ammonia. Also, we already have the infrastructure to handle ammonia in terms of the terminal and the tanks. Also, ammonia is much easier to work with than hydrogen, and it has already a regulation and a logistic network established and everything. And also, we're connected to a very important industry, which is mining, that is very focused on trying to decarbonize, so it will be a big help to decarbonize the blasting part of the mining. And also, we have already completed the pre-feasibility study because we started working in this about 3 or 4 years ago, and now we're entering the feasibility stage. Now, I told you that this is very costly because it's a small scale and we're not in 2030, we're in 2021, but still, even though without any sort of subsidy or grant, the total impact per pound of copper is between 1 and 2 cents of a dollar per pound of copper. Remember that copper is today above $4, so it's very little. Still, we're doing every single effort possible to lower the number, and today, with the support that we have gotten, we're already sure that we can lower the number to half of it. So 0.5 to 1 cent of a dollar per pound. What are we doing to try to move forward with it and to get the support? We're working with some local agencies to get funding for pilots, for first phases, to get the wheel rolling regarding green hydrogen. We're applying for a $20 million fund from them. We're working together with the licensors and the techno partners and the techno companies in order to have it more efficient, try to fund synergies and see if they are able to get some sort of grants for their equipments. Also, we have been working together with international institutions to get support, and we already confirmed the participation in our project for IFC from the World Bank. They will be co-developers and they will be equity partners for this first phase and the second phase of the project, and they will also be able to bring some grants. And of course, we're partnering with the mining with the local mining industry to be able to be part of the first off-takers for the first green explosives, and some of them also want to be part of the co-development and equity of the first phase of it. So where are we today? We're moving into feasibility stage. It's going to be based on 3 legs: technical, environmental, and financial. We're working together with ENGIE. They are our partner on this since the beginning of the project, the IFC from the World Bank, and some strategic partners from the mining industry and techno partners. The idea is to start feasibility stage now in January. It will last for about 12 to 15 months. It will have a cost of $2 million. And then, if things look good, we will make a final investment decision by the end of 22 and start building to have the first tons of green ammonia and green explosives during 2025. Thanks a lot for your interest, and I really hope that we can make it real and have the first tons of green ammonia in the near future.